So now we continue with how to find solutions of these homogeneous second order linear ODEs with constant coefficients. So with constant coefficients, we mean that, remember that our second order linear ODEs are of this form with the second derivative, first one, and the function u that we don't know. And then we have these coefficients, these functions in principle. But okay, now we are in this particular case with these coefficients are just real numbers, okay? And to really have a second order linear ODE, we ask the first coefficient a not to be 0. Because otherwise, if it's 0, this term is not here, so we have a first order linear ODE. Okay, so let's see if we can solve this equation. Motivated by the first order case, where we only have, let's say, this part, in this special equation, u prime equal to lambda u, where lambda is a real number, we can solve this by hand. Imagine that, okay, if we look at this equation, the function u equal to 0 is a solution, right? But okay, it's not super interesting. So we want a non-trivial solution, which is a solution that is not all the time 0. So we can divide by this u here. And then we can rewrite this as the logarithm of u, well, the derivative of this, and then integrating, we get a constant and a variable x here. And then when we get rid of this logarithm here, we have ux equal to ec plus lambda times x, which is this new constant and this function. So what we are trying to say is, we can choose this constant equal to 1, let's say. So we get this solution, e to the power lambda x. So this is a first order linear ODE, and we get this solution, e lambda x. And now we want to solve this second order linear ODE. So motivated by this, the easiest case, let's say the first order case, we say like, okay, I have no idea how to solve this, but what if I ask the solution to be this form, this exponential lambda x? So we suggest this solution, and during the whole course we are going to see some methods to solve equations, which doesn't mean that this is the best method, the only way to solve the equation. Is just something we can do to get a solution of the equation. And not every equation would need the same method, or not every method would work for any equation. So we have to detect when to use each method. Okay, so we suggest a solution of this form, this exponential form, e lambda x. Okay, so what we need to do is, okay, I'm proposing this type of solution. If this is a solution, it has to verify the equation, right? So what we do here is just, plugging in this solution into the equation. So wait, not that fast. Ux is here. So, sorry, u is here. then the derivative of u, by the chain rule, we have lambda here. So this is the derivative of u. And the second derivative of u is lambda squared e lambda x. So now we have this term in common, this factor in common in the three terms. So what we do here is just get rid of this factor. And we can do that because this is not equal to 0 for every x in R. So dividing by this value, we get this equation, which is quite similar to the original one, right? For our second order linear homogeneous equation is here. And look at the equation that we get. It's exactly the same. Well, not exactly the same, but quite similar, right? Just replacing u by 1, let's say, u prime by lambda, and the second derivative of u by lambda squared. Okay, but this is how we get this equation. And this equation has a name, the characteristic equation. So, what we are saying here with this procedure here is that our candidate of solution, our suggestion of solution E lambda x, is a solution to our second order linear homogeneous equation with constant coefficients if and only if lambda is any root of this equation. Okay, so this is our super important conclusion. And now we have cases, right? We know how to solve this type of equation. We know that this type of equation can have two real solutions, two complex solutions, one solution with multiplicity 2. So we divide these three cases and see what happens. Okay, so here are the cases that I just mentioned. We have the roots are distinct and real, the roots are distinct and complex, or we have only one root with multiplicity 2. So let's see what can we say about this. First case, the two the two roots different and real, which means that these two exponentials are solutions. Then it's an exercise to check that these two functions are part of, form a fundamental set of solutions. So any linear combination of these two is a solution, and moreover, this is the general solution of our equation with C1, C2, any real numbers. Okay, so and then in each exercise that you find this situation, you just can use this result. That if you know that you are working with a second order linear homogeneous ODE with constant coefficients, this part is important, that these are numbers, with constant coefficient, you can use this method, which is the characteristic equation method, and you know that if your characteristic equation has two real roots different, then you automatically know that the general solution has this form. It's the sum of this in a linear combination about these two between these two exponentials. Okay, second case. We have complex roots, and since the characteristic equation has real coefficients, these two complex numbers are related because one is related with this minus, let's say it's the conjugated of the other one. So basically we have these two real numbers involved, alpha and beta. And okay, what we just did before tells us that E lambda 1 is a solution and E lambda 2 is a solution, but we don't like this, right? Because they are complex solutions and we would like to have real solutions. So we don't like this, but there is a way to get real solutions from these two complex solutions. If we rewrite this solution as E alpha x, E I beta x, and here we use Euler's formula, which is this identity here with these red squares, and we know that this can be written as the cosine of beta x plus the sine of beta x. Okay, and we do the same for the second solution. Doing the same, we have here minus beta, sorry, the cosine and the sine, but now we know this property of this function. Sine is an odd function, so this minus can go here, and cosine is an even function, so this minus disappeared. Okay, so basically we have the first solution written in this way, the second solution written in this way. Now, let's see if you remember, we have these two solutions and we have that any linear combination between these two is also a solution because we are working with homogeneous linear ODEs. Okay, so we will choose, here is what I said, we don't want complex solutions, we want real solutions. But okay, using these linear combinations, we can get two real solutions. For instance, if we choose one half as constant, and then 1/2 minus 1/2, and we take those two linear combinations, we get these two real solutions. You can check, then you can do the calculation. So finally, the two real solutions are E alpha x cosine beta x, E alpha x sine beta x. Okay. Third case. Sorry, the general solution. Okay, so now the general real solution, in this case where we have two complex roots of the characteristic equation, is here we have this E alpha x and any linear combination between the cosine of beta x and sine of beta x. Okay, again, you can use this result each time you are working with the second order linear homogeneous ODE with constant coefficients, and the characteristic equation has two complex, not real roots. Okay, third case and last one. When we have only one root with multiplicity 2. So here there is a way to find, okay, so one solution is given by our suggestion, and we have another solution that for those that are interested, we can discuss how to get it, but it's not part of the program, so let's just don't say too much about that. But we can verify that this is another solution. It's exactly the same exponential, but here we have an x. X times this exponential. Okay, so someone comes and says like, okay, you know, this one is the one that you already know because of the method that you were using, and here you have a second one, and now we have to believe that, and we can check that is a solution. And you can also check as an exercise that these two guys form a set of fundamental solutions. You can also check that. Okay, so the general solution in this case, where we have only one root with multiplicity 2, is the linear combination, any linear combination between these two functions. Okay, so conclusion. The general solution of a second order linear homogeneous ODE with constant coefficients is given by the combination of these two exponentials when the roots are real and different. This combination, linear combination between cosine and sine of beta x and this exponential here when the roots are complex and have this form. And finally, same exponential but one with an x in the front when we have only one root with multiplicity 2. Okay, so this is the first conclusion. We can also apply this characteristic equation method to solve higher order linear ODEs. So far we only saw this method applied in this second order ODE. So what if we want to apply this method to higher order ODEs? Let's see what happens in an example. Okay, so we have this. Third derivative, so order 3. We are still linear, constant coefficient, this is a 1, this is a -1, and the other ones are 0. This equation is homogeneous because this is 0 here, so we are okay. How did we start before talking about this method? We said, well, okay, we know the solution of the first order of the first order ODE. A certain first order ODE is this exponential, so we suggested this a solution of this form to the second order ODE. Okay, so we do the same here. We have this third order ODE, and we suggest, we just try if this exponential e lambda x is a solution of our equation. Which values of lambdas verify that this is a solution of our equation. So we do exactly the same. We plug this function in the equation. So here is u, and here is the third derivative of u. Again, we know that the exponential is not 0, so we can get rid of this term, this factor, sorry. And we get this, which is again called the characteristic equation. Okay, now if we look for the roots of this polynomial, we get lambda 1 equal to 1, and then two complex roots, these two. So what we have here is that, what we have here is that this lambda 1 will give us this solution EX, and then each time I find two complex solutions, I put them together to find these two real solutions. So in some sense, once we have the roots of our characteristic equation, we can just, for each quadratic equation, use the previous result, this conclusion here. Okay, so these two complex roots, where this is alpha and this is beta, give us this two real solution, E minus x over 2 cosine of this number time x, and same exponential here and the sign of this number. And sorry, I think this is some Spanish missing here because it's sign in Spanish is doesn't matter. Okay, so going back to our example, we have this third order ODE, homogeneous, with constant coefficient, and we found these 3 solutions, right? So we have third order ODE, 3 solutions. You can check as an exercise that this set of 3 functions form a set of fundamental solutions. But okay, anyway, we can conclude that the general solution of our example is any linear combination of these 3 functions. And this is how we apply the characteristic equation method when we have higher order linear ODEs. Okay, so we propose this as solution, we find the characteristic equation, we find the roots of the characteristic equation, and basically we recycle our conclusion here each time I have this type of situation. There is a remark to be done, because remember this third case where the root is only 1 with multiplicity 2. Okay, that's maybe the hardest case, but just a remark to say about that. If we have a real root of the characteristic equation with multiplicity m, then we propose solution of the forms: the exponential with only lambda, same exponential with x, same exponential with x squared, and so on and so on, same exponential x minus 1. It's exactly what we did in our case where we have a second order homogeneous ODE, where we have a root of multiplicity 2, and we have this exponential as a solution, and 2 minus 1 is exactly 1, so we have these 2 solutions. But what I'm saying here with this remark is, imagine that they have a root with multiplicity 3, then we would have this 3 first function. With multiplicity 4, okay, this 3 plus x to the power 3 and the same exponential, and so on and so on. Okay, so just to have in mind this remark. Okay, example, I'm not sure if it's the last one, but okay. We have here an ODE of order 4. So here the highest derivative, constant coefficient, this is a 1, this is a 5, 9, 7, 2, so we are okay. Homogeneous, we are in the right setting. Okay. In this case, we compute the characteristic equation. Remember plugging in this candidate exponential lambda x as a solution, and we find this equation. And after some computations, we know that this is the factorization of the equation. So here we have lambda equal minus 2 and lambda equal minus 1 as roots, but this minus 1 has multiplicity 3. So this lambda 1 minus 2 will give us this exponential minus, sorry, it's not lambda here, wait a second, so this minus 2 will give this solution, minus 2x, exponential minus 2x, and this lambda 2 minus 1 with multiplicity 3 will give these 3 solutions. So the first one is the easiest, just the exponential minus x, the one that we, let's say, is obvious from how we get them. And then we go to this remark and say, okay, then consider this other one with x in the front and the x squared in the front. And that's what we did. And what you can conclude later is, you can also check if you want, it's not mandatory, that these 4 solutions give us a fundamental set of solutions. Remember how to do it. It's in the first part of the lecture. Okay, so the general solution of our equation is any linear combination with these 4 functions where these numbers are real numbers. Okay.